All right. So thus far in this course, we have been concerned with how to set up the theory of quantum mechanics, if you will, the theoretical underpinnings of quantum mechanics. And from today, we will shift gears slightly and we will start talking about what quantum mechanics does for us. All right. So largely speaking, the postulate one of quantum mechanics tells you that every physical system is described by a state vector, and the time evolution of the state vector is governed by the Schrodinger equation. Excuse me. So the Schrodinger equation is given by ddt of psi is h psi. Okay. So notice that I'm writing a partial derivative because a state vector is a function of both x and time. So sometimes this is called the time dependent Schrodinger equation. So TDSE, the time dependent Schrodinger equation, because there is an explicit dependence on time. Now I will write this equation in the position space in the x basis. Okay. So if I write it in the x basis, the above equation is basically I have to take the inner product of this guy with x equals x h psi, right? So the left hand side is nothing but IH bar d psi dt, where psi is a function of both x and t, equals, and in the x basis, the representation of the Hamiltonian is simply d square dx square plus v of x. So the left hand side, sorry, the right hand side is basically minus h bar square over 2m d square dx square plus the potential energy. Remember, not v of x hat, but just v of x, because we are in the x basis. So any function of the x operator can be simply replaced by the corresponding function of x. Okay, so this is the Schrodinger equation, the time-dependent Schrodinger equation in the x basis. All right. So now we want to understand. So if we want to say anything at all about any physical system, we have to learn how to solve this differential equation. Okay. So let us solve this differential equation by means of what is called a separable solutions method. Okay. The first step in the separable solution method is a rather mysterious step. I'm going to write this psi of x comma t as some function that depends on x alone times some function that depends on t alone. So I'm going to write this as some function that depends only on x times some function that depends only on time. Okay, at this point, any curious student should ask, how is this even valid? How can you write down the solution as something that depends only on x times something that depends only on time? You are throwing away a whole lot of other possible solutions. For example, I can have a solution like sine of xt. Why not? Right? Okay, with some constant here to balance the units properly. But this is a perfectly valid function, and it could well be the solution of the time-dependent Schrodinger equation, and this doesn't fall in this bracket. Right? I cannot write sine of xt as something that depends on x alone times something that depends on t alone. Right? Or I can think of a host of other functions that don't fall in this category. So how am I justified in choosing this separable solution method? Hold on to this question, and I'll answer this question toward the end of this lecture. This is a very important question. Okay. Notice that this is not the only way of solving the Schrodinger equation. This is one of the possible ways. When I discuss a little bit about Fourier transforms, I will also try to solve this equation using Fourier transforms, and I will show you that you get the exact same solution. Okay, so for now, let us take this ansatz as granted. This is an ansatz, and I'll plug this in equation 1. Okay, if I plug this in equation 1, what do I get? Notice that whenever I have something like d psi dt, the ddt only acts on the phi part because the chi doesn't know about time. So I can write the d psi dt as chi of x times d phi dt. Notice that my partial derivative on the left-hand side has become a total derivative on the right-hand side because phi is only a function of one variable. Okay. So substituting this ansatz into the first equation gives me IH bar, the left-hand side is only a function of, only a derivative of time. So I'll pull out the chi and write the left-hand side as d phi dt. The right-hand side has a spatial derivative. The spatial derivative only hits the chi. It doesn't know anything about the phi, so I can treat the phi as a constant. As far as the spatial derivative is concerned, and I can write this as minus h bar square over 2m. And since chi is only a function of x, I can write this as a total derivative, d square chi over dx square plus some function of x times chi. Okay. Now, I'm going to divide both sides of this equation. Okay, I'm going to divide both sides of this equation by psi. Divide. And this very simple step actually helps us to solve this equation remarkably. Divide both sides by psi, which is equal to chi times phi. If I divide both sides by chi times phi on the left-hand side, the chi goes away and I get 1 over phi of t d phi dt equals, on the right-hand side, the phi goes away and I get only chi something like that. Now, if you stare at this equation, something becomes rather obvious to you. The left-hand side is only a function of time. It has nothing that depends on position. Similarly, the right-hand side is only a function of position. It has nothing that depends on time. Okay. Now, what does this mean? So it means that you have an equation in which the left-hand side depends only on one variable and the right-hand side depends only on the other variable. There is no term anywhere here that is a function of both x and t. There is no mixed terms, which means if I change time slightly, the left-hand side changes because it's the explicit function of time. The right-hand side does not. Now, how can that be? If I change the time and if the left-hand side changes, if this equation should be valid for all possible values of time, if I change the time and the left-hand side changes, the right-hand side should also change. But the right-hand side does not know anything about time. Similarly, if I change position, the right-hand side changes, but the left-hand side does not, because the left-hand side does not know anything about position. So the only possible way in which this equation can be true for all possible x and all possible t is if they are both just a constant. Okay. The left-hand side is also a constant, the right-hand side is also a constant, and they are both equal to the same constant because they both have to be equal to each other. Okay, so which means this very simple ansatz of separable solution method has actually decoupled a second-order differential equation that is a function of two variables into two equations. The first equation is IH bar 1 over phi of t d phi dt is equal to a constant, and this constant I will call E for reasons that should be obvious in a second. And the right-hand side is also equal to the exact same E. E squared chi over dx squared plus v of x chi. This is also equal to E. Okay. So since I've called that equation 1, I'll call this equation 2 and 3, but I'm going to rewrite equation 2 and 3 in the following fashion. So I'll rewrite the first equation as d phi dt equals, so you can minus I E over h bar. And the second equation I'll call this equation 2. The second equation I can rewrite as minus h bar square over 2m d square chi dx square plus v of x chi of x equals e times chi of x. This I'll call equation 3. Okay, and I'll box equation 3. And I will solve equation 2. The solution of equation 2 is rather straightforward. There should be a 5 here. 5. If I integrate equation 2, what do I get? d phi by phi integral equals minus IE over h bar integral dt. The solution of this is logarithm, and this is just minus IE over h bar times time plus some constant, which means I can write down the solution for the time part. This is just a e to the minus IE over h bar. Okay, there we go. That's it. We have solved the Schrodinger equation as far as the time variable is concerned, because we have decomposed the solution into something that depends only on x times something that depends only on time, and we have solved for the time part. Unfortunately, this is as far as we can go. We cannot solve equation 3 unless we know the physical system which we are investigating, right? And that makes sense, because that it should depend on the forces that are acting on the system. It should depend on, in other words, it should depend on the potential. So if I'm given the potential, then I can solve equation 3. Okay, so as far as this stage is concerned, talking about the general solution of the time-dependent Schrodinger equation, this is as far as we can go. So we can claim that we can solve for the time dependence of the wave function, which is given by e to the minus IE over h bar t, and the spatial part should be gotten after solving equation 3. Equation 3 is called the time independent Schrodinger equation. Okay. Hopefully this terminology should be familiar to you. If not, don't worry about it. It's actually very straightforward why we call it that. There is no explicit dependence on time, and the wave function chi is only a function of x. So this is called the time independent Schrodinger equation. And that is pretty much it. So we have solved for psi of xt, can now be written as a e to the minus iet over h bar times chi of x. And once you give me the potential, I can solve for chi of x by solving equation 3, the time independent Schrodinger equation. And I know what the solution of the Schrodinger equation is, the time dependent Schrodinger equation is. Okay. So this is basically some trickery in differential equations. But now certain questions and comments remain. So I'm going to write down a set of comments. Okay. 1. How on earth is this solution valid? How on earth is this on sorts that you can always write the solution psi of xt as some function of x alone times some function of t alone? The answer to this has to do with the fact that the Schrodinger equation is a linear equation. The time-dependent Schrodinger equation is a linear equation. What does this mean? A linear equation simply means that if there are two solutions, psi 1 and psi 2, if there are two solutions, psi 1 and psi 2, then a linear combination psi equals a psi 1 plus b psi 2 is also a solution. This is the principle of linear superposition. What does this mean? Well, let's investigate. So psi 1 and psi 2 are solutions of the time-dependent Schrodinger equation. So I can write down two equations, IH bar d psi 1 dt equals, I'm simply going to write h psi 1. I don't want to write the entire thing again, because I simply want to prove this to you. I can also write the exact same equation for the second solution, h psi 2. Okay. All right. Now, if these both equations are true, is psi, which is a general linear combination of psi 1 and psi 2, also a solution? Is psi also a solution? Well, let's find out. So multiply the first equation by A and the second equation by B and add them up. So the first equation is IH bar A d psi 1 dt is H A psi 1. Remember, A is a constant, so I can put it anywhere I want. The second equation, B d psi 2 dt equals H A psi 2. And now let me add both of the equations. So the first equation can be written as IH bar d dt of A psi 1 plus B psi 2 equals, on the right hand side I have H acting on A psi 1 plus B psi 2. I can clean this up by writing A psi 1 plus B psi 2 is my solution psi, so IH d psi dt equals H psi. So if psi 1 and psi 2 are solutions of the time-dependent Schrodinger equation, then a linear combination of them is also a solution. I can extend this to any number of linear combinations. If psi 1, psi 2, psi 3 are solutions, then A psi 1 plus B psi 2 plus C psi 3 is a solution. Okay. Now, so let us assume that it has arbitrary number of solutions, which means that I can write down. So let us call these solutions with some index n. Okay, let us say psi n of x comma t is equal to a e to the minus I e n t over h bar chi n of x. Okay, there can be as many n's as one, so there can be like 15 different solutions, whatever it is. Then I can always write down a linear combination psi of x comma t, which is a general linear combination of a n, or rather, so I'll put that n here also, because the constant can be different for the different solutions. There is nothing that says that it has to be the same constant for every solution. So I can construct a general linear combination. Okay. And I'm guaranteed that this general linear combination of all these solutions is also a solution. Okay. So let me box this guy. And this is the, excuse me, this is the most general solution of the time-dependent Schrodinger equation. And now this should answer the question as to why this separable solution on sorts is valid. Even though each one of the solutions is of the form chi of x times phi of t, a general linear combination will not be of the form chi of x times phi of t. Note that the general linear combination psi of t is not necessarily of the form some g of x times some f of t. Okay, which means the general linear combination of all these separable solutions contains within itself all possible solutions of the time-dependent Schrodinger equation. That is why we are justified in starting with the separable solution on sorts, simply because of the linearity of the differential equation, the differential operator that we are investigating. Okay, so it is the linearity of this differential operator that tells us that any linear combination of solutions is also a solution, which means the most general solution does not have to be of the separable solution form. A combination of separable solutions can look completely different. Okay, and we have encompassed all possible forms of solutions using this answers. So I'm going to call this equation 4, and this is a very important point. Okay, so this is the principle of linear superposition. So this is the first comment. The second comment has to do with interpretation and the notion of stationary states. Stationary states. Okay, what are stationary states? Well, stationary means something doesn't change with respect to time. But obviously the solution is time dependent, right? All this psi of x comma t has a time dependence here. But what is actually stationary is the combination psi star psi. Okay. So remember that when we talked about the interpretation of this, we said that the quantity psi square dx is the probability of finding the particle described with the wave function psi in an interval dx. Okay. Now, if you properly normalize the solution, then minus infinity to infinity mod psi square dx has to be equal to 1. Okay. Now, stationary in this context simply means that even though psi is time dependent, mod psi square is time independent, because mod psi square, which is psi star psi, is given by a e to the minus I e n t over h bar chi n of x star times a e to the minus e n t over h bar chi n of x. Okay. So this is equal to the e to the plus I e n t over h bar times e to the minus I e n t over h bar simply becomes equal to 1. And this is simply chi n star of x chi n of x. And this is indeed time independent. Okay. So this is the sense in which you should understand these stationary states. Each one of these solutions, psi n of x comma t, which is a n e to the minus I e n t over h bar chi n of x, is thus called a stationary state. Okay. So not just that, if you calculate the expectation value of any observable in this stationary state, let us call expectation value of any q. This is equal to integral psi star q psi dx, where this q is in the x representation. Okay, and I'm assuming minus infinity to plus infinity, unless otherwise stated. And as long as this q does not depend on time explicitly, if q does not depend on t explicitly, then this expectation value can be simply written as mod a square chi n star of x q chi n of x dx, which means the expectation value of any observable in these stationary states is also not time dependent. Okay, so that is also an important point to note. Now, notice another important point. This is only has to do with the stationary states. Remember that the capital psi, which is a general psi, a linear superposition of stationary states, is not in general a stationary state itself. Okay, this is important to understand. For example, let me say that there are two solutions, psi 1 and psi 2, with energies E1 and E2. Okay, then the linear superposition of these states is A1 e to the minus I E1 t over h bar times chi1 plus A2 e to the minus I E2 t over h bar times chi2. Notice that this is not a stationary state. Why? Because if I calculate psi square in this state, what is this? This is equal to A1 e to the minus I E1 t over h bar chi1 h bar chi2 star times the same thing again. Okay, and this is explicitly time dependent because there are cross terms. So you will get terms like mod a1 square mod chi1 square plus mod a2 square mod chi2 square, but you would also get terms like a1 star a2 chi1 star chi2 e to the I e1 minus e2 t over h bar plus the complex conjugate a1 a2 star chi1 chi2 star e to the minus I e1 minus e2 t over h bar. Okay, so even though the expectation values of dynamical observables are not time dependent in the stationary states, they are time dependent in the most general linear superpositions. Okay, so how do the expectation values change? Well, let us calculate. Suppose if I'm calculating the expectation value of an observable Q in the most general linear superposition of stationary states. Okay, how would I calculate this? This is equal to, again, integral psi star q psi dx minus infinity to infinity. Okay, this by itself is time dependent because psi star psi is also not time independent. So I have no reason to expect that the expectation value of q is also time independent. So let me calculate the rate of change of this expectation value with respect to time. Let us calculate ddt of q. Okay, ddt of q would be, now I'll apply the chain rule. Psi star is time dependent, q is in general time dependent, and psi is also time dependent. So I have three terms on the right hand side: minus infinity to infinity d psi star dt q psi dx plus psi star dq dt psi dx plus integral minus infinity to infinity psi star q d psi dt dx. Okay, now notice that I'm using partial derivatives inside because capital Psi is a function of both x and time. Okay, and I'm only taking the derivative with respect to time. Now I know that the general linear superposition of stationary states also obeys the time dependent Schrodinger equation. So I can have IH bar d psi dt equals h psi. Okay, and if I take the complex conjugate of this equation, minus IH bar d psi star dt equals, now since Hamiltonian is Hermitian, I will only have h psi star. Okay, now plug that in. Instead of d psi star dt, I can write minus 1 over IH bar h psi star. So the first term becomes ddt of q equals minus infinity to infinity minus 1 over IH bar h psi star q psi dx plus integral minus infinity to infinity psi star dq dt psi dx plus psi star q h psi dx. Okay, now when all is said and done, you can actually show that this actually simplifies into a very neat form. And the result of this is actually called what is called the Ehrenfest theorem. And this tells you, let me actually derive it instead of saying it in words. Sorry, I made a small mistake here. When I take the complex conjugate, I should write this as psi star h. So I'll write this as psi star h. And I can club the first term and the second term together, and I will write this as minus 1 over I h bar integral minus infinity to infinity psi star hq minus 2h psi dx. And the middle term is nothing but minus infinity to infinity psi star dq dt psi dx. And this guy is nothing but the commutator of h and q, right? So I can write this, and if I sandwich any operator between psi star and psi and integrate, I'm taking the expectation value of that particular operator. So I can write this as ddt of an operator q equals I over h bar is the expectation value of h and q plus the expectation value of the explicit time derivative of q. Okay, if q doesn't depend on time explicitly, then the last term is 0, and I will only have the commutator of h and q expectation value. And this result is called Ehrenfest theorem. Okay. Let us apply it to some specific operator, like let us say q equals the momentum operator p. Okay. Now what do I get? The left hand side is ddt of p equals IH bar expectation value of the Hamiltonian and p square over 2m. And since p doesn't depend on time explicitly, sorry, Hamiltonian and p. And since p doesn't depend on time explicitly, the last term is 0. So what is the commutator of h and p? Well, the commutator of h and p is the commutator of p square over 2m plus v of x and p. And since any function of p commutes with p, this is essentially v of x p. Okay. Now, how do you compute this? Well, let's go ahead and compute this. So to understand what this commutator is, let us act it on some test function. So v of x p, and I'll use the x representation. So I will use minus ih bar ddx for p, and I'll act it on some test function. This is equal to v of x minus ih bar ddx commutator of x. This is equal to minus ih bar v of x df dx, that is the first term, minus ih bar ddx acting on v of x times f of x. So this is equal to minus ih bar v of x df dx plus ih bar. I'll take v as a constant and write this as df dx, plus the second term is plus ih bar f of x dv dx. Okay. Now notice that the first term and the second term cancel cleanly, and you get this is equal to ih bar dv dx times f of x. Now I can remove the test function f of x on both sides of this equation, and I can write this equation as the commutator of vx and p is ih bar dv dx. So plug that in the Ehrenfest theorem. What do I get? ddt of p equals I over h bar times expectation value of ih bar dv dx, which is equal to minus dv dx. Okay. Now, if you stare at this, you will find something quite curious. This is nothing but Newton's second law in classical mechanics. The time rate of change of momentum equals the negative gradient of the potential, which is the force. So it tells you that in quantum mechanics, even though we have constructed a completely different theory based on completely new postulates, the expectation values in some sense behave like classical observables do in classical mechanics. But before we read too much into this, let us postpone this discussion to a separate lecture, and I'll talk about when the context of the harmonic oscillator, I'll talk about what are called coherent states, and we will understand the connection to classical mechanics and these expectation values, time evolution of expectation values in a bit more transparent fashion. But notice that this curious fact does fall out of Ehrenfest's theorem, that the expectation values follow classical equations of motion in some sense. So we'll understand this a little more in the context of coherent states later. Okay. So this is the second comment that I wanted to make about stationary states. Okay. And the third comment, and a rather very important comment, has to do with setting up of what is called the continuity equation in quantum mechanics. But before I forget, let us note that these stationary states are also states of definite energy, which should be obvious. Okay. So I will use this as homework. You should prove this yourself. Stationary states are states of definite energy. In other words, if I calculate the dispersion of the Hamiltonian in this state, sigma h square, which is h square minus h square, this is 0 in stationary states. Okay, remember that we discussed that the standard deviation is a measure of the dispersion. So if I get a whole bunch of values, then what is the measure that tells me how different every particular value is from the mean value? And in stationary states, every value is the exact mean value. All these values are exactly the same. So if I calculate the expectation value of the Hamiltonian in a sample of identically prepared stationary states, I will get the exact same value of Hamiltonian operator, eigenvalue of a Hamiltonian operator, which is the particular energy of the stationary state under question. So this is a very important property that you should prove to yourself. So take this homework seriously and do this. It's actually a very, very simple exercise. Once you understand how to calculate expectation values, simply sandwich the Hamiltonian operator between two states, psi star and psi, which are stationary states. The third comment that I want to make, the last comment for today's lecture, is the notion of a conserved current or a conserved probability and the setting up of what is called the continuity equation. Okay. Now, for those of you who remember a little bit of electromagnetism or who are studying electromagnetism currently, in electromagnetism, there is conservation of electric charge. Whenever there is a conservation of physical quantity, there is an equation that describes this particular conservation, and that is called the continuity equation. Excuse me. In electromagnetism, the continuity equation reads, the rate of change of the charge density, rho is the charge density, is equal to minus del dot J. Okay, this is the charge density, and this is the current. Current can be thought of as rho times the velocity for in some sense, right? And del is the del operator, which is the right hand side is basically dj dx plus djx dx plus djy dy plus djz dz, which is the divergence of the current. There is a similar equation in quantum mechanics for probability. Remember that we argued that psi square is a measure of finding the particle. Psi square dx is a measure of finding the particle in some region dx, right? Which means I should find the particle somewhere, so the total probability has to be equal to 1. So if I want the probability to be conserved, then I have to set up a corresponding equation for the probability change. So in other words, if I look at the quantity size mod psi square, which is psi star psi, I can interpret this mod psi square as psi star psi as some kind of rho in quantum mechanics. Okay. which means I have to write down an equation that tells me how this psi square, which is psi star psi, changes with respect to time. So in other words, I have to set up an equation for ddt of psi star psi. Okay, what is this? This is equal to psi d psi star dt plus psi star d psi dt. Okay, but both psi and psi star obey the Schrodinger equation, so I can write down what d psi star and d psi are. IH bar d psi dt is h psi, and assuming that I'm writing everything in the position representation, x basis, and minus IH bar d psi star dt is psi star h or h psi star, depending on however you want to write it. So this is equal to d dt of psi star psi equals so I want to get the IH bars correctly, so I'll write this as psi times d psi star dt, which is minus 1 over IH bar psi star. So the position representation really doesn't matter if I write this way or that way. So I'm going to write this as the second term is a plus psi star 1 over IH bar d psi dt can be written as h psi. Okay. So this should be written as minus 1 over IH bar. If I take out common, the first term is, or I take 1 over IH bar out common, excuse me. This is equal to psi star. H is basically in the position representation d square dx square plus v of x acting on psi. The second term is minus psi d square dx square plus v of x acting on psi star. And you would actually find that the second term cancels because psi star v psi minus psi v psi star are the exact same things. So this whole thing boils down to 1 over IH bar, if I get the signs correct, minus h bar square over 2n times psi star d square psi dx square minus psi d square psi star dx square. Okay, and this is equal to minus h bar over 2ni psi star d square psi dx square minus psi d square psi star dx square. And I can write this quantity, interestingly enough, as, remember that if I want to set up a continuity equation, I need a derivative of some vectorial quantity on the right hand side. Now, since I'm working in just one dimension, so it's hard for me to set this up as a vector, but I'll show the generalization very easily. This can be written as d dx of psi star d psi dx minus psi d psi star dx. Why? Because if I take the derivative of psi star d psi dx, I get d psi star dx times d psi dx plus psi star d square psi dx square. And the mixed term, which is d psi star dx times d psi dx, cancels between the first term and the second term. So you can actually show that this is equal to this. Sure. Okay. So anything I write in blue, you should show yourself. This is rather easy to show. Okay, which means I can write the left hand side. If I call this quantity h bar over 2mi times psi star d psi dx minus psi d psi star dx as some kind of a probability current. Then then I can write this whole thing as d dt of psi star psi equals minus d dx of j of x. This is my rho, or in other words, d rho dt equals minus dj dx. Okay. Now, if I want to write this as a proper vectorial quantity, I should understand how this equation would look like in 3 dimensions. In 3 dimensions, of course, the right-hand side looks exactly the same because the definition of rho does not change, but the definition of j would simply be h bar over 2mi psi star. Now, instead of just differentiating with respect to x, I should have differentiation with respect to x, y, and z. The natural extension of this is with respect to the del operator. So this is del psi minus psi del psi star. Okay. So there's an equation that operates in quantum mechanics that tells you that the probability is conserved, and this equation is the exact same, has the exact same form as the continuity equation in electromagnetism. This is the continuity equation in quantum mechanics that tells me that d rho dt plus del dot j vector, this is obviously a vector, equals, because this is a vector, 0. Okay. This is a fundamentally beautiful and clean equation that tells me that there is a dynamical thing. In this case, the probability that is actually a conserved quantity. Whenever there is a conserved quantity, you will have a continuity equation in physics. This is a ubiquitous equation in physics. Okay. So, for example, in people who do thermodynamics and they study mass flows, they always write down a corresponding equation that tells you that the total mass is conserved as long as the mass is not lost, etc. So the setting up of continuity equation in quantum mechanics tells you that quantum mechanics, being a probabilistic theory, still obeys the fact that the probability is a conserved quantity, and so you can always set up this continuity equation in quantum mechanics. And the next lecture will move on to study a little bit more about Fourier analysis, and we will set up what are called wave packets. And these would be very essential for us to understand the quote unquote simplest case in quantum mechanics, the case of a free particle. But this is a subject of tomorrow's lecture, and today I will stop at this point.